Okay, and what we're going to study in this lecture is called Pascal's principle, and it says any change in the pressure applied to a completely enclosed fluid is transmitted undiminished to all parts of the fluid in the enclosing walls. So a great example of this is a hydraulic pump, or a hydraulic jack, where you have a small force in a small area, which then transmits to a very large force in a very large area. Now the distance that you have to push this plunger can be very large compared to the distance that this plunger on the right hand side will move up. But in Pascal's principle, what we basically are saying is that the pressure over here on the left side has to end up equaling the pressure on the right side. It's a conservation of pressure. Now the second picture is interesting, where the pressure on the left-hand side equals the pressure on the right-hand side. And this pressure that's acting on this piston comes from two places. It comes from this force acting on this particular area, force divided by area, but also it equals this pressure for this fluid height, rho GH. This fluid height is helping to push on the bottom of this piston here. So we have this statement that says an external force F1 is applied to the piston on the left. As a result, a force F2 is exerted on the cap of the chamber on the right. And B just shows the hydraulic car lift. So what Pascal's principle states is that the pressure in area 2 equals the pressure in area 1. And since pressure equals force over area, it's exactly what we have is F2 over A2 equals F1 over A1. So if we rearrange this equation to solve for F2, this force here that's acting on this piston, we get force 1 times A2 all over A1. So we have this practice problem here that says that in a hydraulic car lift, the input piston has a radius of 0.012 meters and a negligible weight. The output plunger has a radius of 0.15 meters. The combined weight of the car and the plunger is 20,500 newtons. The lift uses hydraulic oil that has a density of 800 kilograms per meter cubed. What input force, F1, is needed to support the car and the output plunger when the bottom surfaces of the piston and the plunger are at the same level, and for B, the level shown in figure 11.15b with H equaling 1 meters. So what we have here is this picture. Question A is asking us to find F2 when the two are at the exact same height. And then question B is asking us to find F2 when the heights, this height is different. This height, there's a height here. And actually, they're not asking us to find F2. They give us F2. They want us to solve for F1 in both cases. They told us that F2 is 20,500 newtons. So if we go back to the problem, we end up saying that F1, using the equation we learned before, F1 equals F2 times A1 over A2, pi r squared over pi r squared with the different radii. Plug in our values, and oh, by the way, the pi's cancel. Plug in all our values, and so the force that we need is 131 newtons on the left-hand side. Now how do we deal with it when we have that liquid height? Well, what we say is that pressure 2 is equal to pressure 1 plus rho GH, with pressure 2 equaling force 2 divided by pi r squared, that's the area, and pressure 1 is force 1 divided by pi r squared, which is the area. This is the height of the liquid, so we have the pressure 1 on the left-hand side plus the liquid. So what we end up with when we use P2 equals P1 plus rho GH, we plug in for P2, F2 plus pi r squared equals F1 all over pi r squared plus rho GH. So we're taking into account, remember, this is on the left-hand side. This is the pressure from that small piston plus the pressure from the height of the fluid that gives us our pressure here acting on the car, the 20,500 newtons. This is our force there. We then go ahead and solve for F1, plug in all our values, the pi's cancel there. So we go ahead, plug in all our values, and we end up with 127 newtons. So what we've learned in this particular lesson is that Pascal's principle states that the pressure on the left-hand side equals the pressure on the right-hand side. You have to take into account all pressures that are occurring, whether it's from a force or from the height of a liquid, but the pressure on one side equals the pressure on the other side.